Hey, Robert. Good luck with this. Okay. What'd you say? Yeah. I won't be here tomorrow, Robert, but Max said he'd help you. All right. The easiest way. The easiest way I know to tell you to do related rates is just to do it. Oh no. Oh my goodness. Let's do it. Just do it. I'll show you my technique on how I approach these. These are all word problems, and you really just have to decipher. I always draw a picture, and I always list out my information. I'll always come to the side of the problem. After I'll read through it one time, I'll draw a picture if I can, and then I'll write, what have they given me? What do I need? And I kind of write that and list it out so that I can see. So let me give you an example. These are very time consuming. Now, related rates, a relate, remember, is a what? It could be a fraction, but it's a derivative, right? I'm derivative. I'm thinking like dx dt, and most of these are dt because they're in time, right? How is x changing over time? Or d theta dt, how is the angle changing over time? So we're looking at how rates relate to one another, and that's what makes it really confusing. Yeah. Oh, yeah. But we're gonna have some little relay rates problems sprinkled in here. Okay. A hot air balloon rising straight up from a level field. Okay, I'm gonna go ahead and draw that. Hot air balloon rising straight up from a level field. Here's my field. I'll try not to get too artistic for y'all. I don't want y'all to feel bad about y'all's artistic skills when you see mine. Yeah. A hot air balloon rising straight up from a level field is tracked by a rangefinder 500 feet from the liftoff point. Okay, so here's my rangefinder, and I'm just interpreting this information. This is the easiest way I know to tell you to do it. 500 feet. How fast is it rising? Angle of elevation or angle of elevation depression? Kind of yes, but kind of not. Okay, yes it is. This year. At the moment so that tells me instantaneous. Yeah. Shut up, yeah, babe. Copy. Because I paste. Okay. All right, try it now. Refresh. At the moment that the rangefinder's elevation angle, there you go. So whenever I see the word moment, I know I'm talking about instantaneous. That makes me think what? IROC, which is derivative, right? All right, so at the moment that the rangefinder's angle of elevation is pi over 4, y'all agree with that? That's the angle of elevation. Is it there now, Cannon? It says 11:14, not 11:15. I got the date wrong. The angle is increasing at a rate of 0.14 radians per minute. Now, before I ask the question of the problem, what is 0.14 radians per minute? The derivative what? Give it to me in like these terms. D theta, because this is radians, and that's what my theta is measured in, right? This is d theta over time, right? Because it's radians per minute. Do y'all see how we got that? This is theta, this is t, so d theta dt is 0.14. Is everybody okay there? Sure? Okay. How fast is the balloon rising at that very moment. Okay, so what do we have? Okay, you're right. I'm thinking around a SOHCAHTOA thing. All right, let's think. Here's what I do. Here's what I think about whenever I do these. I think about what do I have? I don't like that. What do I have and what do I need? Okay, this is how I approach these problems every single time. What was I given? What do I have? I'm given theta. Theta's pi over 4, right? I'm going to give some variables here. What should we call that? Give it a variable, b. We'll call this b. B is 500. Agreed? If I call that b, I'm going to call this a. I also have d theta dt, and that is 0.14. This is speed. This is radians per minute. What do I need? What are they asking me for? How fast is the balloon rising at that moment? Okay, so velocity of what though? The balloon rising, what? Look at the picture. What's representing this, the height? What about the height though? You said the speed or the velocity, so how do I find speed or velocity of a variable? The derivative, right? So this, how fast this is rising, is going to be dA dt. So what do I need? I need dA dt right at that moment. Is everybody okay? All right. I have to, remember how we talked about when we were doing the optimization, I've got to relate everything together so that I can get just one variable so I can take a derivative. This is kind of the same thought process. Somehow, some way, I've got to use what I've got and do something to where I can have an a in there so I can take a derivative and get dA dt. So I have to think some way to relate one or more of these with an a. I can always take a derivative, but what am I going to do? Notice I have a derivative of theta. So if I use theta in it, I could do that. So can you think of anything that would relate? I'm not even solving the problem yet. Right now, I'm just trying to relate all these variables together. What I need, it's got to have what I need in it, and then I got to include some things that I have, or I can use the things I have to create that. So look at the triangle. Look at what I have. Obviously, this is a right triangle, right? Because angles of elevation are right triangles here. Okay, so that would be my first inclination to a squared plus b squared equals c squared. If you use that, I've got two unknowns here, right? If I solve that for one of them, it's not going to get me where I need because I've got b, I need a, so that's another, I'd have three unknowns, right? So that's not going to do me much good right here. So let's think of something else. This is what you have to do with these problems. You've got to reason through. Okay, so which one of the so, the co, or the toa are you going to use? A is the opposite. Agree or disagree? Okay. And B is the adjacent. So which one? We need the tangent. So would you agree that the tangent of theta equals opposite over adjacent? Now, anything that's changing that's not a constant, I want to keep the variable in there for right now. But there is one constant in this equation, and what is it? B, 500, right? Where that range thing is sitting, he's not moving. Now, he's looking up, so theta's changing, right? But he's always going to be 500 from the base of liftoff. So I'm going to replace this B with 500. Now, look at what I need. I'm doing all this so that I can find this. What could you do? times 500 on both sides. So I get 500 tan theta equals A. Now what? Well, so here's the thing. Since it said, and this is where you have to think, you want the derivative at that instant. Well, what's changing? That's changing, right? So I want this derivative to be when theta equals pi over 4. So I'm finding a general derivative, but then I'm going to do it at a specific point a little bit later on, if that makes sense. So let's find the derivative right now. Let's find the derivative just of this. What is the derivative of 500 tan theta? 500 secant squared theta, but remember I'm doing this with respect to time, right? Remember how if we take the derivative of y, we have to follow it with a dy dx? I'm taking the derivative of theta with respect to time, so I have to chain it with a d theta dt. And then I am going to find the derivative of a, but again with respect to time, because I'm looking for a speed, right? I'm looking for feet per minute or feet per hour, whatever. Okay, we're confused. Okay, what am I trying to find? Look at what I'm trying to find. A derivative with respect to time, right? So I'm taking the derivative with respect to t. Normally I take it with respect to x, right? So if you just have 2x, the derivative is just 2. But if I had 2x plus y with respect to x, it's 2 plus, I can't just put 1, I have to follow it with dy dx, because I have to follow it with the variable that I'm taking with respect to. So here I'm taking with respect to t, so I have to, I'm really doing implicit differentiation is what I'm doing for all of these. I just don't have an actual t in my equation. You with me? Okay. Again, right, 1 dA dt. All right. Now, it says at the instant that theta is pi over 4. Well, look, I can plug in this. I can plug in this. And now I can find dA dt. So 500 secant squared pi over 4 times 0.14 should give me dA dt. Pi over 4 square root of 2 over 2. If I flip that, I get 2 over square root of 2. If I square that, you're probably doing this on your calculator. That's okay. I get 4 over 2. I got 2 for this. I got 500, bless you, times 2 times 0.14. You get what? You should get 140. Yeah. 140 what, though? Remember what it was I was trying to find? A is in what? Okay, feet per, is it minutes? In the beginning, because it was 500 feet. The terribly awful thing about these are none of them are the same. So you can't just memorize a technique with these. You really have to dig in on these, and they are. Huh? You'll have 1 or 2 on them. We're going to practice with it. This is what I was going to do a little project with. I was going to have you create your own, do a little drawing with it, and solve each other's, but we ran out of time. Okay. All right, let's do another one, huh? That's your final answer. You found what they asked you to find. What do you think that? I'm also here pushing you in the right direction. It's hard when you start looking at them and go, oh my. That's why I said for me, I have to have this and I have to have a picture. I have to. All right, let's do a little bit of an easy one before we jump into a hard one. This is secant is 1 over cosine, so 1 over cosine of pi over 4 squared. But make sure you're in radians. Always be in radians from now on. Just always stay in radians for calculus. Because otherwise, you really start messing up. And they're buttholes. They'll put the degree answer on a multiple choice. If you're in degrees, it should be in radians. Because buttholes.
So we know never to put a degree answer.
Right.
Even if you have to guess.
Well, I mean, like, they'll put, if your calculator is set to degrees instead of radians, they'll put that as one of the, yeah, so, yes, it would be marked wrong. I know.
Why does it have to be in those?
All right. This was a typical related rates problem. Like, I have seen ones like this more than one time on an FRQ that are worded exactly. It's a hot air balloon, right? Like, this is a typical, a right triangle using either a trig function or Pythagorean theorem is so very typical. But there are others that are also frequent. So I'm glad you asked that. This is number 8. How'd you know? For something like that, yes. But to know what you need to, like, we had to figure out that that was using the tangent or whatever. No, you won't get that, but you'll have to deduce that for yourself. I know. Yeah.
So we need more.
Yeah. This is tough stuff. Pi r squared. Heating a plate. When a circular plate of metal. That's a good circle. It's a little bit smushed at the top, but side. Is heated in an oven, its radius increases at the rate of. So what does that mean? What's radius increases at the rate of? Derivative of what? The radius with respect to time. So dr dt, so the radius increases at the rate of 0.01 centimeters per second. Okay, so it's in the oven and it's growing. The radius is increasing at that rate. Okay, every second it's growing 0.01 centimeters. At what rate is the plate's area increasing? When r equals 50. What is the question? That's what we got to determine first. What is it we're trying to find? If they say at what rate is the area increasing? The derivative of the area. So what do I need to find? dA dt. What was I given? I was given dr dt. And I know when, so what am I trying to find? I'm trying to find dA dt when r equals 50. Not at any, remember, derivatives are at instantaneous points. So at the exact time when the radius is 50, so I'm expanding. When I hit 50, how fast is it increasing? Because it could increase faster or slower, right? Say right, because it could. Like we're not at a constant increase on our area. It might be that it starts doing this and then it starts getting faster, the hotter it gets. You know what I'm saying? So the second it hits 50, how fast was it increasing then? That's what they're asking. That's all. That's all the information I have. What are you going to do? That's exactly what I would do. I would go, okay, well, I know that the area of a circle is pi r squared. This one's a little bit easier than the balloon one. What can I do? I would take the derivative the way it is right now, right? Because I'll know r. Now, this is kind of the tricky part. This is where everybody stumbles around a little bit sometimes. This is not plugged in until the end after I take the derivative, okay? And the reason is because that's my instantaneous. What rate is it changing at this point? That's when I plug in at the end. So here, if I take the derivative here, I get dA dt equals what? 2 pi r, that's it? So you're taking it with respect to r? dr dt. Why dr dt? I'm taking the derivative with respect to time, right? Unless this bottom variable matches the variable you're taking the derivative of, you have to chain it with a d whatever dt every single time. So see how I need something dt? Unless I take the derivative of t itself, I need to follow with d whatever dt. So if I was, let's say this was circumference and I did pi d, I'd need to do dc dt equals pi dd dt. Everything has to follow with a dt. All right, so let's fill in what we know. We don't know this, that's what we're looking for. 2 pi, do I know the radius? Well, I do. I want to know this at the time that r is 50, so I'll go ahead and plug in 50 here. Do I know dr dt? What is it? 0.01. So it's just pi. What are my units? And be very careful. This is area. Right now we're area. Squared. Square centimeters per second. 100. 2 times 50 is 100, and 100 times 0.01 is 1. So at the exact moment that that plate's radius is 50, the whole area of the circle is increasing pi square centimeters every second. That's the answer. Thought that was easy? Want to do a hard one? Yeah, this one was from your homework too. Well, you got a few extra of these I'm going to sprinkle in there. A spherical balloon is inflated with helium. It's because he answered it, if you ever answer them. At the rate of 100 pi cubic feet. This one might be too easy too. We'll keep going with it. That's volume, but it's a rate. So tell me what that is. dV dt. How did you know, Lainey? Cubic feet is volume. Per minute is my time. So it's volume, time, volume, time. Everything I take, I'm going to take with respect to time. All of these are going to be respect to time because I'm comparing rates. All right. How fast is the balloon's radius increasing at the instant the radius is 5? So how fast, that tells me derivative, right? How fast is the radius increasing when r equals 5? So what am I looking for? This is what I have. This is what I need. dr dt. What I need is dr dt. What I have is dv dt. And I know when r equals 5. What shall I do? How am I going to relate these variables? What's the volume of a sphere? I feel like it's 4/3 pi r cubed. They would definitely give you this because I always forget them. Four-thirds pi r cubed. For one like this, they would say, given that the volume of a cube is 4/3 pi r cubed, and then they would proceed to say, or at the very end, they would say, assume that the volume of a cube is, yeah. We can find the derivative just as it is. We need to do a hard one. I'm glad y'all don't think this is hard, though, because it's still hard because it's related rates. You think it's hard? Okay. It is. It really is. dV/dt equals, let's see, if I multiply that around, I get 4 pi dr dt. No, r squared. Sorry. I did the power rule. And remember, well, pi's a constant, right? And this one's a little bit different. This one I need dr dt, so I'm going to have to rearrange a little bit. I'd plug in first, and then I'd rearrange. So I know dv, and by the way, this could be negative. If the air was going out, that would be a negative 100 pi, right? But because it's going in, then it's increasing. You have to really read the problem. That's exactly right. All right, so it's what? No, it's not. They got 1. Let's see. dV/dt, so 100 pi, did you put 100 pi there? 4 pi, 5 squared dr dt. 25, that's 100 pi equals 100 pi dr dt. What are my units? Feet per minute. Look at the units of r, look at the units of t. That's going to be my unit. Yeah. So make sure you can interpret this and you understand what it is we found. At the exact moment that the balloon has 100 pi, or that the balloon is increasing at a rate of 100 pi cubic feet per minute, the radius is increasing 1 foot per minute. So for every foot it increases, the volume increases 100 pi. Does that make sense? You ready for a doozy, and then I'll stop and let you work. They gave it to me. They said that this was cubic feet, so that means yeah, it's feet. A trough, this is number 20. A trough, and let me see if I can draw this. It's a triangular prism. No, this is drawn for you on here, and I still can't draw it. Okay, I don't know. I don't even know. Do what, Lainey? Joyce, you're making me nervous. Okay, yes, draw it.
I'm gonna try my own experiment, okay?
Oh
my god, this thing is hard to work.
Go.
You're welcome.
Thank you.
I've never taken an art class.
Okay. I'm gonna I'm going to do the same thing, but I'm going to put it up here because I saw the picture. I see what you're doing, though. I'm going to do it this so you can see. Yeah. Okay. You get the point. Yeah. Yeah. I couldn't get the end right, though. Okay. I'm going to put all the labels on here. So this is water. Funny. And they have this diagram for you, and that was very nice of them. It's purple water because why not? And this is flowing in from a little pipe here. Yep, Joyce, that's a pipe. And it's flowing in. Y'all like I'm done with your pictures? Just give me the page number because I'm done. Page 265. All right, this is 15 feet long. It is 3 feet tall. This little piece is 4 feet here. And the water right now is 2 feet. All right, the water. The water level is 2 feet, but the whole trough is 4 feet tall. All right, so a trough is 15 feet long and 4 foot across, which I've drawn on here as shown in the figure. Its ends are isosceles triangles with heights of 3. Water runs into the trough at a rate of 2.5 cubic feet per minute. How fast is the water rising when it's 2 feet deep? So that was already on the picture here. Holy crap, what am I doing here? What in the world am I going to do? It's a little similar, yes. First thing I need to know is, I definitely see this is, and again, I tell y'all how I tackle these because this is just how I reason through them. The first thing I see is I know I'm dealing something with what? Volume. So first thing I'm going to do is how do I find the volume of this shape? So volume is generally the area, especially if it's like a symmetric shape like this, the area times the height, right? So I could do the area of this triangle times the height of it. And you don't know how to get area. Okay, so I feel like, well, okay, so let's look up triangle, maybe this triangular prism, because they would definitely give you this as well. So don't feel bad about looking up a volume equation. That's the length. So this length here, right? Because the area of the triangle times the height. Think about it standing up on its side. If you're talking, because remember I told you area times height. Does that make sense? So the area of the triangle times how high it is will give you the volume. All right. Now, remember how we always have that one variable that it's find this when this happens? This is my when. Okay, so that's my one that's varying. That's not a constant. So I'm not going to include that as I take derivatives or anything. That's going to be one of the things I plug in at the end. Can I just take the derivative the way it sits? Actually, tell me what I'm trying to find first. How fast is the water level rising? Derivative of something. What am I trying to find? Not volume. All right, so I'm going to call this level here. Let's give that a variable. W for water. W for water. So I need dW dt. Oh dear. How am I going to relate all this together? Somehow I got to get a W somewhere in here, right? How am I going to do that? What do we have? We have length, we have base, we have height. We have all of this. We just don't have it related to a W. So how are we going to relate it back to it? And we have dV dt, right? That's how fast it's flowing in. Okay, so now what do we do? I'm thinking we make this the W. Okay, because here's why. Oh, not that one. H, sorry. Sorry. And here's why I'm thinking that, because the volume, we're finding it at a specific point. So I'm thinking that's my varying one. The volume varies based on that. No. Listen, they're all this confusing, I'm telling you. Like, you have to reason through them. They weren't, but this one and the shadow, the balloon, the shadow problem, and then coffee filter problem. Oh, dear Lord. Okay, let's see what happens if I change this. If I say that this is W, or I say that this is H, whichever you want to do. Let's find the derivative here. Okay, now remember, whenever we take derivatives, we talked about things being constant whenever we take derivatives. This 15 feet across is not changing. That's going to be 15 regardless. Do you agree? So would you also agree that no matter what the height of the water, the volume, like I think what I'm trying to explain to you is what I'm finding is the volume of water, not the volume of the trough. Okay, so the volume of water would be 1/2 base, right? That's changing here. That's going to have to change. Times W, but then the length stays the same. Well, but is the base 4 when you're here at this level? If you've got it for the water, if I'm talking about the volume of the water itself, the volume of water in the correct. Because as it rises, that changes. Okay. 15/2 dW. If I do this though, I'm still going to have too many variables. I still got to find a way to relate it. Stacy, way to pick a stupid. Well, it is hard. Oh my gosh, I know what it is. We have to set up a ratio. The ratio of height to here is always 3:4. Okay, we won't go into this. I can already look at y'all's face. Let's wait until we get to one that's hard. Do it hard on the spaghetti. Do it hard on the spaghetti.
We're gonna do a hard one.
It's not impossible, but here, let me just explain. So there's a couple where you have to make a ratio for them. So in other words, if this is flowing in at a steady rate, then the ratio of 3 to 4 is changing at the same rate as well. So 3 to 4 is my ratio of the, wait, what's 3? 3 is W because that's water. Water to. So that would be 3B equals 4W. Well, the point is, remember how I told you you got to relate the variables you got to something? So now I could solve this. Remember what I'm trying to find? I'm trying to find dW dt. So in this case, B would be 4/3 W, and I could plug that in here, and now I could take a derivative. Now it's an easy problem to find dW dt for. (3060 over 6 W squared). Robert, I'm really sorry. So now take the derivative. dV dt equals 20W dW dt. And I'm trying to find it. Now I can fill in what I know, right? I started out with dV dt. What was it? 2.5. And it said when W is 2. So what's 2.5 divided by 40? I took the derivative here. Hard. Thank God I got the same answer that they got. 0.0625. They obviously did it without calculator because they got a fraction, but I did not. What are my units? W's in feet. Well, you're dW dt. Remember, you're the water. I don't know. Okay. Feet per minute. Hey, we did it, y'all. Oh my goodness. It was a good problem solving one to do because did you see when we hit the wall on this one and when I had to stop and think about it? Well, were you?
I was all the way up until you made your own ratio. And I get
Okay.
why you made it, but
Okay, so if you get to any point, like I knew I had to use, I knew I had to use the volume equation, right? That was a given because that volume was given to me. And I knew that the volume involved all of these, but there was absolutely no way, if I take the derivative, I knew whenever I took the derivative of this, I was going to end up with a dV dt, a dB dt, and a dW dt. And if I look back at what and I don't know what the exact, it doesn't even matter what these, I just know whenever I do it, I'm going to end up with those. And when I go back to plug in, what did I have? I didn't have both of these. I had this one to plug in, but I didn't have that one. So I was going to be in a bit of a pickle trying to plug in. So what I had to do was figure out how can I relate B and W some way to each other. Right. Yes, yes. Right, because you got to find some way, and maybe that relation is Pythagorean theorem if you're in a triangle, right? Maybe you can do an a squared plus b squared equals c squared and relate, but some way you got to figure out a way to relate those variables to each other. For this, the only thing that I saw as I looked, and I only saw it when I looked at the picture. If I just read this problem and didn't have a picture, I'd have never made the connection whatsoever that I needed a ratio. But looking at this, I'm thinking, what's happening? And literally, you have to stop and think. You got to stop and look at the picture and reason through it. How in the world? I know this is changing. I know this is changing. If I have those values, if it's steadily decreasing, right, those have got to be changing at the same rate. So it's a ratio there. This is the B. This will be the W. Yes. If it's completely full, then it's 3 and 4. But we're not looking, remember, we're finding the volume of the water, of a certain level of water. So it's not always 3 and 4. These are changing. As it rises, those change. That's why they had to have a derivative, because they have to have a rate of change. Okay, but two, you'd have to plug in and, right. Well, 2 and 3 correspond to each other, right? 3 would be what it is if it's completely full. 2 is what it is at that instant. So 2 is what you're plugging in after you take the derivative. Because remember, we're looking at an instantaneous rate of change. That's after we find the derivative and we plug in. So the only reason that I have this 3 and 4 is so that I can set up that ratio to relate the two variables. But 2 and 3 are the same. It's just one's the water and one's the hot. Yeah. These are tough. Don't get bogged down on them too much. I'm going to leave you some to start tonight. What time do we get out of here today? How did that go so stinking quick? We didn't even have a homework problem.
Well, we didn't really start so much.
Oh, that's my bad. It's kind of exciting. I'm putting a few problems in here, and everything's going to be due Monday, not Friday now. Everything, this too. And Friday, you need what? And Friday, I will have enough done where you can ask me any questions on Friday, because I'll be back Friday. But this is all, I'm not going to leave any plans for y'all tomorrow now, because you got the review and you got this. Yes, just work. Yes. Let's do 9. No. 14. Let's do 2 more. 16 and no. Yeah. One more. Let's do 33. And you got a couple of them in that review too that you already have. Robert, may the odds be ever in your favor, buddy.